Okay, let us continue with a few more clamping circuits in this video. So in the previous video we have seen the clamping circuit which is having a diode in this direction, and we assume that VD1 is equal to 0 volt. We are considering ideal diode. We found that the positive peak is now clamped to 0 volt, and the output voltage V0, the positive peak is clamped to 0. So we shall see when we actually saw in the previous case. So when we are assuming the VD1 to be 0, the capacitor voltage was charged to the peak voltage, that is VP. So let us consider the second circuit where we are assuming the VD on, that is a diode as a typical diode which is got a VD on voltage as 0.6 volts. Now under these circumstances the capacitor voltage will not charge up to VP, so it will be charging only up to VP minus VD on, because this VD1 we are considering it as 0.6. If you are assuming the peak voltage as 10 volt, now it will be 10 minus 0.6, it will be charging to only 9.4 volts. Now we know that the output voltage under steady state is Vin minus Vc. So the Vin is the sine waveform which is having a sinusoidal waveform with a peak of Vp and negative peak of minus Vp. Now the output voltage can be easily written as Vin minus Vc. So from which we can clearly observe that the positive peak is now clamped to Vd on. So in the previous circuit, so where we assume the Vd on to be 0, the positive peak was clamped to 0 volt. Now the difference is now the positive peak is now clamped to Vd on. So there is a major difference. Again, the peak to peak of this input is 2 Vp. Here also the peak to peak of the output voltage also 2 Vp. Now the V0 that is output waveform is one where the positive peak is now clamped to Vd on. We should see one more circuit here. So this is an improvised circuit compared to the previous one. Now here we have a reference voltage VR. Now we should see the difference between the first, second and third. In the first one we didn't consider any reference voltage, the VD1 was 0. In the second circuit there was no reference voltage, VD1 was taken as 0.6. Now we are assuming a third circuit where we are considering a diode and reference voltage. Now if we assume the VD1 to be 0, this reference voltage as VR, which is 2 volt. Now this capacitor will not charge up to Vp now, it will charge up to Vp minus VR. So that's what is under steady state, the capacitor voltage will be charged to Vp minus VR, meaning the output voltage now is input minus VR. So you can carefully observe if the output peak to peak is 10 volt, that is 5 is positive peak, minus 5 is negative peak. Above 0 is a pure sine waveform, which is AC signal having positive and negative halves distributed equally above 0. You can observe the output. So now the output positive peak is clamped to reference voltage, that is 2 volts. Now this voltage, the positive peak is clamped to now VR. So whatever the reference voltage we have kept here, the positive peak is now clamped to VR. So that's why the name clamping circuit. Now we are trying to clamp the positive peak of the input voltage to a reference voltage VR. If this reference voltage is 1 volt, this positive peak is now clamped to 1 volt. Now since it is 2 here, it is clamped to 2 volts. But whatever the clamping level, the output peak to peak still remains as the input peak to peak. In this case it is 10 volt peak to peak. So what happens, let us see in the next circuit, if I reverse the diode, what happens, or if I reverse the polarity, what happens. So in the fourth circuit we should see a circuit where we have, so this is now we are considering a VDN of 0.6. Now it is not, in the previous case we consider VDN to be 0, now it is 0.6. Now we can see the capacitor voltage will be charging to Vp minus VD1 plus VR. Now it was previously charging up to Vp minus VR. Now this to this VR, this VD1 is also get added. The capacitor voltage is now charged to, if you assume this as 10, it is 10 minus 2 plus 0.6. So 2 is of VR and 0.6 of VD on. Now the positive peak is now clamped to VD on plus VR. So now if you assume VR to be 2 volt, now the positive peak is clamped to 2.6 volts. Again the peak to peak remains as 20 here, which is the same peak to peak of the input voltage. What is the difference between the third circuit and the fourth circuit is, in the third circuit we assume the VD-on to be 0. It was clamped to VR. Now we are assuming VD-on to be non-zero, which is 0.6. Now it is now clamped to VD-on plus VR, which is 0.6 plus 2 volt, which is 2.6. Now we shall see next circuit where we have the diode direction is similar to the previous case, but we have a battery which is reversed in its direction. Now what is the capacitor voltage under steady state is, the capacitor voltage is Vp minus of this VR minus VD-on. So sorry, this is VD-on minus VR. So why it is minus VR is because we have the polarity of the reference voltage is being get reversed. It is Vp minus VD-on minus VR. So in the previous case you might have observed that it is VD-on plus VR, because this was plus minus, this was also plus minus, it was being get added. Now in this case it is plus minus for VD-on, whereas for VR it is minus plus. The capacitor voltage is now changed to Vp, that is the peak voltage, minus of the voltage that is over here, which is nothing but VD-on minus VR. So this is what is the capacitor voltage. Now looking into this, so we can clearly see that the output voltage is Vin minus Vc. Now this positive peak is now clamped to, so this is the voltage. So as you can see now the positive peak is now clamped to VR minus VD-on. So since sorry, it is VD-on minus VR. This is the voltage to which the capacitor is charged. It is Vp minus VD-on minus VR. Now if you carefully observe, the positive peak is now clamped to VD-on minus VR. So VD-on is 0.6, VR is of course it is 2 volt. That negative sign is taken care here. So it is now VD-on, which is 0.6 minus 2 volt, which is minus 1.4. Meaning the difference between the previous circuit and this circuit is, if VD-on is 0.6 and if this reference voltage 0, it will be clamped to 0.6. If you have a 2 volt here, over that 0.6 it will be charged to another, of course it will be clamped to another 2 volt because it is positive. If this reference voltage is positive, above this 0.6 it will be keep on clamping. If this reference voltage is negative, from this 0.6 it will come down by that reference voltage. Meaning in this particular case, so this is 0.6, it was supposed to be here. Now since it is polarity is negative, from 0.6, from plus 0.6 it will come down by 2 volts. So what is 0.6 minus of 2, which is minus 1.4. Assume that this is 1 volt. If this is 1 volt, then it is 0.6 minus of 1, this would have been minus 0.4. Assume that this is 4 volt. If this reference voltage is 4 volts, it is my plus of 0.6 minus of 4, this happens to be minus 3.4. What I want to say is, if the direction of the diode is seeing downwards, if it is P, if this is N, the positive peak will be clamped to the VD-on plus or minus this reference voltage. If the polarity is this, so it is VD-on minus VR. If the polarity is the opposite, that is if this is plus, if it is ground, if the negative is grounded, as in the previous case, as in this case, now it is the positive peak clamped to VD-on plus VR. So this is the major difference in having a battery with a polarity which is of this type or this one. So as we can clearly see that in all the circuits we continue to have the diode direction the same. So it is going down here. So this is P is connected to capacitor, here also P is connected to capacitor, here also P is connected to capacitor. In all the 5 different circuits we consider the diode direction to be same. Only thing is that in one case we didn't have VD-on, the other case we considered VD-on, in one more case we considered a VR and with some polarity, and here VR is with a opposite polarity. In all these cases we saw that the positive peak is now clamped to different voltages. The positive peak will be clamped to either VD-on or VD-on plus VR or VD-on minus VR. So this is the key to note here. So we shall see the same thing in the simulation and try to solidify our understanding. Yeah, this is a circuit diagram to analyze the clamping circuit operation for different reference voltages. So this is the reference voltage, and we have a clamping circuit. The diode direction is P connected to capacitor and the N is connected to ground, of course through a reference voltage, and we have a resistor of 100k. And just have a look at, if you can remember, I can change the reference voltage VR, which is here, by using a dot step parameter. It is now varied from -3 to 3 volt in steps of 1 volt. So meaning that I'm going to apply a reference voltage of negative voltage 0 as well as the positive voltage. Now since VD1 is around 0.65, so we'll see, okay, what are the different different waveforms we're going to get here. Now this is going to summarize three different cases where we are considering a reference voltage of uh, negative 0 as well as the positive values. So let me just simulate and see how does the output waveform looks like. So this is the input waveform, which is ranging, of course, going from 0 to 10 volt. We are seeing the first cycle. Of course, you can carefully observe here. So this I have just simulated for only 2 cycles, but I am seeing it from after 1 cycle, after 1 millisecond, meaning that I am already there into the steady state. I am not seeing from t is equal to 0, meaning that capacitor charging will not be seen now. So whatever capacitor voltage we are seeing will be the steady state voltage. Now the capacitor has already stabilized in its voltage. So that's what is the meaning of time to start saving the data. So we are not seeing the data from 0 second. If it is from 0 second, you can see the capacitor is charging along with the input voltage. So in order to just verify only the transient, the steady state response, we are starting from 1 millisecond, the output observation. So let me just run this and see. So this is the input waveform. So let us see the output waveform now. Now let me just separate the input and output. So let me have a different pane, and let me just have this. Now you can see we have so many different waveforms, and you can see they are all having at a different point. So as we know that, okay, let us try to find out what are these positions. Now the first one corresponds to, now you can see it is clamped to minus 2.3. So can we just remember what is this minus 2.3 now? So this corresponds to this particular circuit, where we consider the reference voltage is actually varied from -3 to 3 in steps of 1. The first voltage that is applied is -3 in the simulation. So the reference, now the output positive peak is now clamped to -3, which is over here, which is 0.6 minus 3. So 0.6 minus 3 happens to be minus 2.4. So that's what you are seeing in the simulation. So the first circuit, the first waveform, if you see here, it is minus 2.3. So we are looking at the positive peak of the output waveform with the first waveform corresponding to a reference voltage of -3. So that's why you can see it is minus 2.3. So let us try to see for a reference voltage of -2 how it looks. For -2, it is now, you can see it is VD1 minus 0.2. So VD1 minus 2 volts. VD1 minus 2 volts happens to be like 0.6 minus 2 volt happens to be minus 1.4. So you're getting almost minus 1.3. So this is for one more point here. So this is corresponding to this is for -3, this is for -2, the red one is for. So let me just only see the output waveforms for more clarity. I can see this is for blue is for -3 reference voltage, is for -2 reference voltage, this is for -1. So -1, we actually get the positive peak is now clamped to VD1, that is 0.6 minus 1 volt. So it is 0.6 minus 1 happens to be minus 335 millivolts, that is almost minus 0.4 volts. Now when the reference voltage is 0, we get, you can see now it is the reference voltage 0, now the positive peak is going to VD on. So let us have a look at when the V reference voltage is positive. When the reference voltage is positive, the positive peak is going to VD on plus VR. Now VD on is around 0.65 plus 1 volt will be 1.63 millivolts. So that's what we are seeing here. Now this is now this corresponds to 1.62. Now the power stick peak is now planned to VD on plus VR.